Hey, welcome to the latest installment of our Ximedica webinar series. Today's webinar will be related mostly to the field of diagnostic and life science instrument development, not necessarily to the broader field of medical devices. So my name is Paul Fleming. I'm a program director here at Ximedica. I lead instrument development programs, and I also serve as the interface between teams that are working on assay development and teams that are developing hardware. So today we're going to talk about automating your assay, maybe more specifically preparing your assay for automation. In the last few years, there's been an obvious trend amongst diagnostic systems towards sample in, answer out systems, or at least sample in, data out systems. And this trend is evident across most diagnostic markets, from those requiring high throughput systems like the Panther Fusion shown on screen, down to those in need of lower throughput instruments like the Luminex Aries. And the justification behind this move is pretty obvious. A fully automated system frees up our valuable lab technician time. It can decrease the chance of contamination in the lab. We can improve reproducibility amongst a host of other advantages. So some solutions are actually out there that don't offer full walk-away automation, and they've still found a place in the market, as long as the most laborious protocol steps have been automated. And you can see that by a number of systems out there that have separate processors and readers. So the question becomes, how do you automate your assay, or where do you start? So you might have a proprietary probe technology, for example, and you're working diligently to optimize that assay. You could be using a combination of commercially available instruments, from pipetting robots to incubators to qPCR instruments, but you want a more streamlined workflow. You want it optimized for your protocol, and the custom instrument really is the only answer there. So, prior to getting that custom instrument developed or starting on developing that, there's actually a lot that can be done to prepare for automation. So, the heading here is don't wait to automate. Really it's don't wait to prepare to automate, but that's not quite as catchy. So, this is really, we're saying that it's never too early to start considering what you need to do to prepare to move to an automation-friendly protocol. So, the first step is to take a look at your current protocol that you've probably developed on the bench in a manual fashion and identify the elements which don't readily lend themselves to automation. One example is to use a chemical lysis method instead of a physical lysis method. That's a pretty widespread technique, and in general, steps like reagent addition, incubation steps are among the easier parts of a protocol to automate. Instead of more physical process like bead beating or ultrasonic shearing, things like that. Another example of a more automation-friendly protocol element is a magnetic bead-based DNA isolation instead of any centrifuge-based ones. And while a centrifuge itself might not necessarily be difficult to automate, they can be quite bulky, expensive piece of equipment, whereas a bead-based isolation protocol can utilize whatever fluid transfer mechanism is already employed in your system, along with the addition of some magnet actuators. And looking around everyday life, we've more and more automation is being implemented, and it's easy to see how kind of slightly different approaches were taken to everyday tasks in order to enable this automation. If we look at a dishwasher, for example, it tells to dry your dishes at the end of the wash, and it does that by using heated air. They didn't try and automate using a kitchen towel to dry the dishes. So the same lesson kind of applies to automation for diagnostic instruments. An approach that may work well in a manual fashion may not necessarily be the best approach for an automated instrument. So after you've assessed your protocol maybe and you've substituted in some more automation amenable steps, you can then start to look at more subtler tweaks that would help the instrument design portion of your development process. One example of this is to examine the various fluid volumes delivered throughout your protocol. In the example shown on the screen, we have a reaction that's comprised of a 2 microliter volume of reagent A along with an 8 microliter volume of reagent B. If we can adjust the concentration of these reagents, it's the potential is there to change this to a delivery of 2 5 microliter volumes of fluid. So you might say, why does that matter? Well, firstly, you've removed a 2 microliter delivery and you've substituted that with a 5 microliter delivery. That can give quite significant improvements in CV with conventional automated fluid pipetting techniques. Secondly, you're now delivering the same volume of each reagent, so you can focus on optimizing for that 5 microliter delivery instead of delivering different volumes. Again, it might seem trivial, but if you're using maybe a non-contact dispense for the reagents, there's quite a bit of tuning sometimes in dialing in for specific volumes, and this can, help a little bit. So it might not necessarily be significant, but depending on how you're automating your protocol, if you're using a microfluidic cartridge, for example, it could be useful for you and your instrument development team to know where some of the protocol can be flexed and changed, where we can push back on some of the things we think are hard constraints. This can allow more options then when considering the automation techniques applied. Some other examples are, can you combine certain reagents instead of storing them and delivering them separately? Or can you use less of the kind of rinse and repeat style steps that are in a lot of diagnostic protocols, wash and dry after ethanol, things like that. Another step then is a mistake we see some people make here is waiting for the custom hardware to be ready before testing out their automation-friendly protocol. You really should try and test it out in a manual fashion first. You don't have to wait for the hardware to be developed. So if you've initially developed your protocol using a centrifuge-based DNA cleanup, there's no reason to wait for the custom hardware to be developed to test how well that works using a bead-based isolation. This can be easily tested in a manual fashion on the bench. This can then provide a better benchmark when assessing the performance of your automated system. Another place that people sometimes wait for their custom automation hardware is when they're miniaturizing their assay. So if you're moving from a 50 to 100 microliter volume for a reaction down to a sub 5 microliter volume, for example, people aren't sure about how they can test that, how they can deliver the reagents, the volumes they want, how they can thermal cycle the volumes they want. The reality is that there are now a host of instruments out there that are capable of handling sub microliters, and they can be used to test the miniaturized assay before you get your custom cartridge or instrument developed. So this basically allows problems to be identified earlier in the development process and solved, more importantly, earlier in the development process. Finally, the last thing I want to touch on is just understanding your requirements. So understanding the requirements for your assay is crucial to streamlining your development process. Moving requirements and moving targets and moving goalposts are some of the big cause of delays in any development process. So in this case, I'm really referring specifically to the requirements that your assay needs to run successfully. A lot of people start off developing their assay using commercially available hardware, which is a great place to start. This is also a really good way to start documenting your baseline requirements. So if you know that your thermal cycler has plus or minus a half a degree accuracy at 95 degrees, and your assay works on that thermal cycler, it's a fair place to start to say that your assay needs plus or minus half a degree of accuracy. This is a great way to get initial requirements down on paper, get them captured, but it should be probed a little bit further where possible. So if you could determine that there is minimal impact on your assay using plus or minus 1 degree of accuracy, it can open up more cost-effective options, different solutions, and provide a shorter development time for your own custom instrument. There's similar scenarios can be presented for different areas of your protocol. From an optics perspective, in the lab, you might be using a $100,000 fluorescent microscope for your detection regime. And this could be far greater than your actual target cost of goods for your instrument. So it can be useful to assess the features and performance parameters of the device you're using and deciding which ones are actually relevant for your assay. This can then, again, allow better hardware choices to be made during the development process. And finally, on requirements, Writing down the justification for them can be a really useful tool to focus in on what's important for your system. It really helps to challenge assumptions that may be in place. So you might ask, why is it important to have a CV of 5% for delivery of a particular reagent in your system? Is it because the CV that your liquid handling robot does 5% when it's delivering 5 microliters? If you're miniaturizing your assay, does a CV of 5% still matter for sub-microliter volumes? Is your assay sensitive to a difference in the range of nanoliters? So, rather than just taking some of these requirements as translate what does 5% CV mean in real terms of volume delivered. You can be surprised about where you can kind of flex and relax some of your requirements a small bit. That can, lead to, again, give you more options for when you're choosing certain elements of your hardware, but it's also capturing these justifications is a really good way to facilitate efficient communication between your assay development team and your hardware development team. And again, that can just streamline your development cycle. So that's all for me touching on this subject. Thanks for taking the time to listen, and I hope you're all able to take something useful from this.